Okay, let's get started. So before we start with today's work, I just want to make some comments on the homework that's been submitted. Okay, quite a few mistakes. So there is still the opportunity to submit and get those points. Okay, I think only one person has gotten the points so far. Okay, for one of the questions. Okay, so firstly, algebraic mistakes. So I'm seeing things like this, where I have e to the x minus x being written as e to the x over x. Okay, so we can't be making mistakes like this. If you're making algebraic mistakes like this, please attend those Saturday classes that go over matric work. Okay, it's very important that you don't make these mistakes, because if you make this mistake on the first line, then every other line below that's going to be wrong. And I can't give you part marks because the algebra is completely wrong. Okay, so please look out for that. The second thing is if we have something like this, e to the x minus x squared over 2x squared plus x plus 1. Okay, so something like the homework problem. I'm seeing students write this top part as infinity minus infinity. Okay, that's not right. Remember what I said? When we're looking at fractions like this of type 0 over 0 or infinity over infinity, you look at the top part as a whole, you look at the bottom part as a whole. This top part is not infinity minus infinity. Okay, infinity minus infinity is if we have something like this first part, e to the x minus x. If you just have this as is, then it's infinity minus infinity. Okay, this expression here is a fraction. It can't be the difference of two infinities. Okay, so please make sure you look back at the table to see what type of indeterminate form you're working with. Okay, the third thing is one of the lines of working was something like this, x over 1 over the natural log of x. Okay, so when you take it down to the bottom to make it type 0 over 0, for example, I've seen taking the derivative on the top and bottom and then getting 1 over x. Okay, again, that's wrong. Look at the bottom, it's 1 over the natural log of x. The derivative of the natural log of x is 1 over x, that part's correct, but this requires the chain rule. You can't just look at the bottom part and see it's the natural log and then write 1 over x. Okay, that is not correct. So d by dx of the natural log of x, this is 1 over x, that is correct. If you have d by dx of 1 over the natural log of x, this needs the chain rule. Okay, so you can't just write 1 over x just because there's a natural log there. Okay, that's not right. Okay, then the fourth thing, there was this question where one of the lines of working was limit x goes to 0, 1 over x. Okay, so that's just going to be taking the limit as x goes to 0, we end up with infinity. I see someone wrote this, and then on the next line they wrote limit x goes to 0 minus 1 over x squared. So they differentiated. Okay, that's not correct either. 1 over x is not an indeterminate form. So we don't have an expression at the top and at the bottom that's 0 over 0 or infinity over infinity. There's no reason to differentiate this. Okay. And even if you were to differentiate this using L'Hopital's rule, you need to differentiate the top and you need to differentiate the bottom. You don't just differentiate the whole line. This is not correct. Okay. So that's just some comments on the homework. If you're making these mistakes, please learn from that. If you haven't submitted the homework yet, there's still a chance to submit and get those points. Okay, again, the due date will be Friday. Okay, so one of the questions was submitted, and that was correct. I'm not going to tell you which one's which. But the remaining homework problems, they're still open for submission. Okay. And again, if you're having issues with algebra or anything like this, please attend those Saturday classes on matric work. Okay, so we're going to do a little bit more on L'Hopital's rule now. So in the last lecture, I said that L'Hopital's rule was a great tool to use. However, we can't use it in all cases. Okay, so there are some situations in which L'Hopital's rule doesn't work. Okay, and we're going to look at the first one now, and that is the limit as x goes to 0 of sine x over x. Okay, so this was one of the examples of an indeterminate form. We see that the top part goes to 0, the bottom part goes to 0, so this is of type 0 over 0. However, if we see a question like this, we can't use L'Hopital's rule. Okay, L'Hopital's rule is not applicable here, and the reason is, if we consider finding the derivative of sine x, so consider d by dx of sine x. Okay, so if we were to use L'Hopital's rule, we would have to differentiate the top part. Okay, and then we'd have to differentiate the bottom part. But what happens if we try and differentiate the top part? We're going to do this by first principles. So this is the limit as h goes to 0 of sine of x plus h minus sine of x over h. Okay, I'll leave you to fill in the rest of the steps here. So this is just by first principles. But eventually we end up with the term limit h goes to 0 sine of h over h. Okay, so just expand this out and then you'll see you end up with this term over here. So how do we evaluate this limit? Well, this is the limit that we're trying to figure out. So we have the circular reasoning here. We're trying to apply L'Hopital's rule to solve the limit, but when we do the derivative, we need L'Hopital's rule again. So L'Hopital's rule, we need to find the derivative needs L'Hopital's rule. We end up going in a circle. Okay, and we can't do that in maths. Maths is one step after another. We don't loop back on ourselves. Okay, so please fill in the steps and you'll see we run into this problem. So L'Hopital's rule cannot be applied. Okay, so L'Hopital's rule can't be applied, but we still need to evaluate this limit. So we're going to have to do something else. Okay, so instead of using L'Hopital's rule, we use something called the squeeze theorem. Have you seen the squeeze theorem before? Okay, so squeeze theorem or sandwich theorem, you should be familiar with that. Okay, so if you're looking this up online, you might see squeeze theorem, you might see sandwich theorem, that's the same thing. Okay, so we're going to do this by first drawing a diagram to see what's going on, and then we're going to apply the squeeze theorem. So we're going to have a limit on the left-hand side, something in the middle that we're trying to find, and then a limit on the right-hand side. Okay. So, just a note, since we're dealing with trig functions like sine or cosine or something like that, usually these proofs come with a circle. Okay, so you should be familiar with your circle geometry if you're doing trig as well. Okay, so we've got ourselves a circle. Then we draw in our triangle here. Okay, let's just, draw that a bit better. Okay, like that. Okay, so this is going to be a unit circle. So we have 1 and 1 as the radii. And then inside here, we're going to have our angle theta. Okay. What we're going to do next is draw in a tangent line that's vertical here. And then connect it up. So there's our tangent line, connect it up like that, and we end up with that larger triangle here. Okay, so with this intersection point there, so the radius is going to go up to that vertical tangent. Okay, so there's a few things that we need to find. The first thing is the area of our triangle on the inside. So let's just shade that in. Okay, so that smaller triangle inside there, we're going to find the area of that. Okay, so let's call that triangle 1. Okay, so we've got triangle 1 there, we want to find the area. Okay, so the area, that's going to be half base times height. The base is 1, because that's just the radius, so half base times height. And the height is the vertical part there, but the vertical part of that triangle is going to be the hypotenuse times sine theta, right? That gives us the height. So that's going to be times 1, which is the hypotenuse, sine theta. Okay, so all those ones, that's not doing anything, so we just end up with 1/2 sine theta. Okay, so that's the area of that smaller triangle there. What we're going to do next is find this area here, including this little curved section over there. So I'm just going to zoom in on that here. Okay, so we've got the arc of the circle, and then we've got that triangle that we worked with inside there. Again, that's going to be 1, that's going to be 1. Now, instead of just that triangle bit on the inside, we want the full section here. Okay, including that little bit that we cut off from the circle. Okay, so how do we find that area? Okay, so imagine we had the full circle, and then imagine that this little section is like a pizza slice, so one slice of the full pizza. So it's something like this. Okay, again, the radius is 1, and we want to find that area there. Okay, now the full area is going to be pi r squared, right? That's the full area of the circle. Okay, but the radius is 1, so it's just pi times 1 squared. Okay, so that's the full thing. But we don't have the full area, we only have a little section of it. So how do we relate the little section to the full area? Okay, we're going to use a ratio. We know that this little section here makes an angle theta. Okay, that's the angle inside there. Now the full angle is 2 pi. If we go around a full circle, we go around a full 2 pi. So if we're only covering theta out of the whole part, then the fractional area that we cover is going to be theta over 2 pi. So part of the angle divided by the full angle, that gives us the ratio. So this is a fraction of the full area, which is pi r squared. Okay, anybody confused with that? Who's confused? Okay, so imagine we've got a pizza, okay, and we've got one slice. We want to find the area. How do we know? Okay, say there's 8 slices. We want to know the area of one of the slices. So it's 1 slice out of 8 slices. So what's the ratio? It will be 1 slice out of 8, so 1 over 8 times the full area. Here we've got an angle theta. The full angle going all the way around, imagine like the 8 slices, so the full angle going all the way around is 2 pi. So we've got theta amount out of 2 pi, so it's theta over 2 pi. It's very similar to what we had with the 1 slice over 8 slices times the full area. So the area of 1 slice is going to be 1 slice out of the 8 slices times the full area. the area of this little section will be theta out of the full angle times the full area. Okay, does that help? Okay, anybody still confused? Okay, yeah, if you're ever confused with these angles and radians, just think back to the pizza. Okay, so the area number 2, that's the area of our pizza slice there. That's going to be this theta over 2 pi times pi, or 1/2 theta. So I've just cancelled the pi's, and the 1's, we don't have to worry about that. Okay, so that's area number 2. That's our pizza slice area. Now for area number 3, we're going to calculate all of this for the extended triangle. Okay, so that is when we take the radius and extend it out, we take that tangent line, extend it out, we get a much larger triangle. We want to find that area. Okay, that's the biggest area that we've got here. Okay, so how do we find that? Okay, so maybe I should leave it for homework. Okay, no, I'll go through it. Okay, so imagine we're taking the tangent of this angle, theta. Okay, so this is a right angle triangle because it's a vertical tangent, makes 90-degree angle. So if we call this top part h, so the vertical part, we call that h, tan theta is going to be opposite over adjacent. So tan theta will be h over 1. Okay, so h is just going to be tan theta. Okay, does anybody not see that? Okay, so that's the height. We don't want the height, we want the area. So area number 3 will be half base times height. That's the capital H that we just found. So that would be 1/2 tan theta. Okay, so we've got the smallest area, area number 1, that was that inside triangle. We've got area number 2, which is the next biggest area, which is that pizza slice we got there. And area number 3, that's the area of the largest triangle that we've got. Okay, and it's in order. Smallest triangle, the pizza slice, and then the extended triangle. So we can form an inequality with this. We've got area 1, that's the smallest part, is less than area 2, that was the pizza slice, which is less than area 3, which was that extended triangle. Okay, so now we're going to start substituting, and we're going to end up with our beginnings for the squeeze theorem. So area 1, that was 1/2 sine theta. This is going to be less than area 2, which is 1/2 theta. This is less than area 3, which is 1/2 tan theta. Okay, but I'm going to write that as sine theta over cos theta. Okay, so that's just arranging them in order. Now each of these terms has a half. We can cancel that. So there, there, and there. Okay, that's all gone. Next, we're going to take the reciprocal of all of these terms. So we're going to have 1 over sine theta is greater than 1 over theta, which is greater than cos theta over sine theta. Okay, so we took the, yes? Oh, yeah, so that doesn't really matter here. So we could put less than or equal to. Yeah, so for the squeeze theorem, remember we're taking the limit. So in the limit, it will become equal to. But for now, it doesn't matter. Okay. Yeah, only in the limit does it become equal. Okay. But that's fine, you can put less than or equal to, that doesn't change anything. Okay, so we took the reciprocal of everything. Now we're going to multiply through by sine theta. So this part will become 1. This will be sine theta over theta. And this part will become cos theta. Okay, now things are a bit reversed. We don't want to deal with greater than equal to. So let's write it the other way. Might be more familiar. So this is less than or equal to sine theta over theta, which is less than or equal to 1. Okay, that might be a bit more familiar. Okay, so now this sets up nicely for the squeeze theorem, because if theta goes to 0, the right-hand side is 1, that stays 1. The left-hand side goes to 1. So the right-hand side and the left-hand side both approach the same limit, which means the center part will also approach that limit. So we have the limit, theta goes to 0, cos theta, limit, theta goes to 0, sine theta over theta, and we have the limit, theta goes to 0 of just 1. Okay, now this left-hand side limit, that's fine. We can take this right away. There's no asymptotes or anything to worry about. So the left-hand side is 1, the right-hand side is 1, so we know that the central limit is also 1. Okay, and that's how we prove the limits using the squeeze theorem. Okay, so just a note on this. If you get a question in the tutorial tests or whatever, something like sine x over x, okay, please don't use L'Hopital's rule. That's wrong. You need to use the squeeze theorem. Okay, or if you come across another proof that also works, that's fine as well. Okay, but this is just one way to prove it using the squeeze theorem. If you find something else, that's fine as well. But do not use L'Hopital's rule. That is incorrect. You won't get any marks for that. Okay. And then the same goes for other limits. If you apply L'Hopital's rule to a limit where you can't use L'Hopital's rule, again, you don't get any of the marks for that. So please make sure you know your limit laws, your limit properties, and the squeeze theorem. All right, any questions on that? Okay, let's move on to some other limits. Okay, so something that's slightly more complicated. Okay, so let's say we have the limit as x goes to infinity of e to the x plus e to the minus x over e to the x minus e to the minus x. Okay, so what happens if we take the limit as x goes to infinity? So we need to check for indeterminate forms. If we have that, then we might be able to apply L'Hopital's rule. So let's see. In the top part, e to the minus x, that goes to 0. E to the x, that goes to infinity. Same thing in the denominator. So we end up with infinity over infinity. Okay, so we can use L'Hopital's rule. Remember, we can only use L'Hopital's rule if it's infinity over infinity or 0 over 0. And in the previous lecture, I showed you how to go from some other form to that form. Okay. So we can use L'Hopital's rule. Let's do that and see what happens. So this is going to be the limit as x goes to infinity, d by dx of the top part, and d by dx of the bottom part. Okay, we're just going to use L'Hopital's rule and see what happens. Here we get the limits as x goes to infinity. The top part, the derivative of e to the x, that's just e to the x. The derivative of e to the minus x, that's going to be minus e to the minus x. And then we're going to have e to the x plus e to the minus x. Okay, so it doesn't look any different to what we had before. Again, if we take the limits, the e to the minus x terms, they go to 0. E to the x, that goes to infinity. So again, we have infinity over infinity. Okay, so taking that derivative didn't do anything. Again, if we take the derivative once more, we see we end up back where we started. So the limits as x goes to infinity. Let's take the derivative once more. Okay. So taking this, we get the limit as x goes to infinity, e to the x plus e to the minus x over e to the x minus e to the minus x. That's exactly what we started with. So we can apply L'Hopital's rule as many times as we want. We just end up going in circles. Okay, so L'Hopital's rule is not going to help us here. We need to try something else. Okay, there's two ways to deal with this. I'll show you both ways. It's good to know more than one method to solve a problem. So, number one, we substitute t is equal to e to the x. Okay, so we make a substitution. If x is going to infinity, e to the x is also going to infinity, so that means t is also going to infinity. So by making the substitution, we can write the limit as t goes to infinity, e to the x, that just becomes t, e to the minus x, that becomes 1 over t, and similarly for the denominator, we end up with t minus 1 over t. Okay, so just a little substitution there. Now, what happens if we take the limit? 1 over t, that goes to 0, t, that goes to infinity, so we end up with infinity over infinity. So we end up with the same indeterminate form that we had at the beginning, but with this one, L'Hopital's rule will help us now. So let's do that. So this will be the limit as t goes to infinity, d by dt, t plus 1 over t, okay, and then d by dt of t minus 1 over t. Okay, so now we can use L'Hopital's rule. Let's take the derivative and see what we get. So this will be the limit as t goes to infinity. The derivative of t, that's just 1. The derivative of 1 over t, that's minus 1 over t squared. And similarly for the bottom. So we have 1 plus 1 over t squared. Now, if we take the limit, the 1 is unaffected, but the 1 over t squared and the minus 1 over t squared, they both go to 0. So this goes to 0, and this goes to 0. And we're left with 1 over 1, which is just 1. Okay, and that is our answer for that. So you see that sometimes L'Hopital's rule isn't enough. We need to do a little bit of manipulation first so that we don't go in those circles. Okay, so sometimes by making the substitution, we can now apply L'Hopital's rule in this case, or you could make the limit simpler. For example, if we had something like this, but with a whole lot of e to the x's, we could make the substitution, and then it makes it a bit easier to work with. Okay, so sometimes you have to make the substitution, other times it just makes it a bit easier to do. Okay, so with some practice, you'll see when you need to do that. All right, any questions on this? Okay, so that's method number 1. Method number 2, some algebra. Okay, so we have the limit as x goes to infinity of e to the x plus e to the minus x over e to the x plus, minus e to the minus x. Okay, so this is another way of handling this problem. Instead of making the substitution with t, here we're going to factor out an e to the x on the top and the bottom. So this will be the limit as x goes to infinity, e to the x, which we factor out. So we end up with 1 plus e to the minus 2x. And then at the bottom, we do the same thing. We factor out e to the x. So we end up with e to the x, 1 minus e to the minus 2x. Okay, so we just factored that out to the left. Now we've got an e to the x at the top and the bottom. That can just cancel. Okay, so let's rewrite this neatly. So this will be the limit as x goes to infinity of 1 plus e to the minus 2x over 1 minus e to the minus 2x. Okay, now let's check if we have an indeterminate form or not. When x goes to infinity, e to the minus 2x, that goes to 0. So that's for the numerator. In the denominator, e to the minus 2x, that also goes to 0. Okay, so we're left with 1 over 1. That is not an indeterminate form, so this is just our answer. So we end up with the limit as x goes to infinity of 1 over 1. That's just 1. So here, we didn't need to do any L'Hopital's rule. So just by doing this algebraic simplification here, okay, factoring out the e to the x, we see we never had to use L'Hopital's rule at all. Okay, we've removed that indeterminate form. Okay, so sometimes you can get around doing L'Hopital's rule just by doing a bit of algebra first. Okay, so please look out for that. Okay, any questions on this one? Yep.
I'm a little bit confused. E raised to minus 2x.
Okay, so let's just do this in a different color here. That's not working. Okay, so just here. So we had e to the x plus e to the minus x. If we factor out this e to the x, we end up with e to the x, 1 plus e to the minus 2x. Okay, so let's just see why this works. So if I distribute this inside, I'm going to multiply the 2. So it's going to be e to the x times 1 plus e to the x times e to the minus 2x. Okay, so that's just distributing it inside. So e to the x times 1, that's just e to the x. Now, whenever we're multiplying terms like this, if they have the same denominator, we can add the exponents. So this will be plus e to the x minus 2x. Okay, that's just from our exponent rules. So x minus 2x, that will be minus x. So this will be e to the x plus e to the minus x. Okay, so what we did here, when we took out the e to the x, that's the same thing as dividing by e to the x and then timesing by e to the x. So if you want to look at it like this, okay, so we had the e to the x and the e to the minus x. Okay, here we're just multiplying by 1. That's not doing anything. But if we take this bottom part here, this will be e to the x. E to the x over e to the x, that's just going to be 1. And then again, using our exponential rules, e to the minus x divided by e to the x. We can take the e to the x at the bottom, we can take it to the top, and it will become e to the minus x. So e to the minus x minus another x, that's e to the minus 2x. Okay, so it's from that division. That's why we get the minus 2x. Okay, is that all right?
No,
Which part are you confused with? The exponential rules?
No, I'm okay with it. There, so e raised to minus 2x.
Yes?
E. who's the euro state?
Yeah, what's the limit? So e to the minus 2x, that looks like this. We're just taking the limit. You did that last semester, right? Yeah, so e to the minus x, when x goes to infinity, this goes to 0. That's just from last semester's work. Okay, so that goes to 0, the other one goes to 0, we're left with 1. Yeah, please make sure if you are not comfortable with limits, please go over last semester's work. Okay. Alright, any other questions on this? Okay, no more questions. Okay, so that's going to be it for L'Hopital's rules and limits. Please make sure you go over your exponential laws, your limit laws, limit properties, and the squeeze theorem. Okay. We're going to start on the next chapter. Okay, so we're done with L'Hopital's rule now. So the next one will be differentials. Sorry.